Hi everybody, my name is Brian Zambry and I'm an Inside Data Engineering Fellow. This is my project, the Global Climate Data Lake and Analysis Platform, otherwise known as GCLAP. So I'd like to start by motivating the project and in particular answering the question, why do we need a climate data lake? And I will do this with an anecdote from my experience as a climate scientist. This is a figure from a paper I recently submitted, and while in the end this figure is just a couple of dots and some error bars, over 100 gigabytes of data went into producing this figure, and not only was it such a large volume of data, but the data came from several different resources. And I'm not the only one to experience this problem in this climate data space. In fact, the National Oceanic and Atmospheric Administration started the Big Data program after identifying that they generate tens of terabytes of data a day, and that while these data are available to the public, it can be difficult to download and work with such large data volumes. So, GCLAP is a climate data warehouse that enables pre-computed and dynamic analysis, has a user interface for easy visualization and download of analysis and results, and overall the idea is to increase the use of data, which is, after all, why it's there. So let's take a look at the GCLAP interface. You can see here we can choose our variable. I'm choosing 2 meter temperature, and you can choose a month or you can choose an annual average. Let's take July, and then we choose the anomaly period, so 2000 to 2019, and then the period from which you want to compute the anomaly, 1980 to 1999. And here we get our temperature anomalies in degrees Kelvin, and we can, if we want to zoom in, we can do so, and then we can also just go up to the corner and we can save this plot as a PNG, and we get our output there. So how did I build this platform? Well, I took the data from several resources, and I loaded it into S3, and from there I used Apache Spark to read and process the data and write it to CockroachDB. Finally, I used Plotly Dash for visualization of the results. And so I originally chose CockroachDB because of its horizontal scalability, and in other words, it's a distributed SQL database, and I'm dealing with a relatively large volume of data, and so I wanted to be able to scale. But in the process of learning about this database, I found out that it actually has its own distributed processing framework. And so one of the things I started to think about and spend some time on is query efficiency. In other words, who should do the work? And so one possibility is that Spark processes all the data and writes to CockroachDB, and in other words, in this case, CockroachDB would just be purely a database. Another way we could do it is just have Spark write to the database and let CockroachDB do the processing with its distributed framework. And a third and final case is using Spark SQL. In other words, Spark processes and handles the queries. And so here are two examples comparing the query efficiency. And so on the left-hand side, we have a relatively simple query, which is annual average, so just averaging over some timestamps. And then we have a more complex calculation like empirical orthogonal function, which is a principal component analysis. And so we can see that for something like an annual average, CockroachDB and Spark perform about the same, and so I decided to just write these data to the database and let CockroachDB do these sorts of calculations. On the other hand, more complicated calculations are more efficiently done with Spark and then written to CockroachDB for quick access. You can see here that Spark SQL is the least efficient in all cases because of the read time of the raw data. And so to summarize this a little more concisely, the answer is that simple aggregation operations like going from several timestamps to a single average are done easily and efficiently by CockroachDB. On the other hand, there are several reasons why Spark is better suited for doing these more complicated computations. So if we take the EOF example again, not only is it a more complex computation, but it's also not as heavy on the write side. So what I mean by this is that in the end, the output for an EOF is just a subset of one single map or one single raster and then a time series. So it's not that much to write and store on the database, and so this is another reason why it's more efficient to do these sorts of computations in Spark. So overall, GCLAP is a real-time climate data analysis platform. It takes care of the painful data preparation process. The UI enables easy visualization and download of results, and again, the idea is to connect data producers to data users. So, a little bit about myself and my journey to data engineering. This is a picture of my wife and me at our undergraduate graduation. At this point, I thought I was going to teach high school math for the rest of my life. I quickly decided that I wanted to do some research, and so I got a master's in applied math and then a PhD in atmospheric science. And over this time, in doing research in several different fields, I realized that it's not necessarily the application that I'm passionate about, but the data itself and the computer science fundamentals. And so here we are now in 2020 on the next hill in the roller coaster of life in my transition to data engineering. I'd like to finish with a shout out to one of our Insight data engineering alum who helped me get my database and load balancer going. Thank you.